Jay Duhan is a master's student here at Waterloo, working on the issues of geological modeling of bedded salts in order to have input into mathematical models of fluid flow and mathematical models for stress analysis that are needed in order to design and in order to interpret information that we collect from the field. So, Jay, the microphone is yours. If you could stand here, the camera will be able to see you. And I do want to remind anyone that is listening in, if you do have a question, just send it to my email and I will try to pose the question to the speaker. Thank you.
Hey, good afternoon, everyone. My name is Jay. I'm an MSc candidate in civil engineering under Professor Maurice Dusseault and Professor Duhan. My topic is geomechanical model in CAES. Well, CAES covers a wide range of topics, so I will not go in technical details in each of the topics, but I'll briefly introduce them. Well, this is a CAES design workflow that Fraser and I prepared earlier this year, and this is also the outline of my presentation. You don't have to read all the words on this presentation, on this slide, because I'll be discussing these. Just focus on the left side, the green boxes. These are the four main phases of the geomechanical model, and these are geology, data investigation, detailed geomechanics, including numerical modeling and numerical modeling analysis, and operating and monitoring. As some of you guys might know, there are actually two main ways of storing grid-scale energy, and these are pumped hydro storage and compressed air energy storage. However, pumped hydro storage is limited due to topography reasons. For example, in Ontario, we have a very flat topography, and we cannot implement pumped hydro here, but we have salt beds, so it gives a good reason for CAES to be successful in Ontario. In North America, there are 8 major salt basins, and you can see them as a black shaded area on the figure on the right-hand side. Number 1 on the top is Mackenzie Basin. This is in the Northwest Territories, and we won't be focusing on them in this presentation. Number 2 is Western Canada Sedimentary Basin. This covers Alberta, which is a good site for Salt Caverns, as Mohammed mentioned in his presentation. Number 3 is Williston Basin. Number 4 is Michigan Basin, which covers part of US and part of Ontario. Number 5 is Appalachian Basin. Number 6 is Atlantic Provinces salt. And those salts are thick. They're actually salt domes. They're thick enough. We can build large salt caverns there, and they're good for CAES. And also in the Atlantic Provinces, they have a lot of wind plants. Number 7 is Permian Basin, and number 8 is the Gulf Coast Salt Basin. Well, in Ontario, CAES are part of the Michigan Basin. As I said before, Michigan Basin covers parts of US and Ontario. Michigan Basin, if you focus on the left-hand side, the figure on the left-hand side, this is a cross-section of the Michigan Basin. Michigan Basin has a ball-shaped geometry. That means the salt beds are thicker in the middle, and on the western and eastern side, the salt beds are thinner and are found at shallower depths. Ontario lies on the eastern side. And on the figure on the right-hand side, we can see that the salt beds in Ontario are in the southwestern Ontario, and they cover major cities such as Windsor, Sarnia, and Goderich. Well, salt beds are part of the Salina Formation. On the stratigraphic column here, we can see that there are 4 major salt-bearing units. And these are units F, units D, unit B, and unit A2. Out of these 4 units, only unit B and unit A2 are thick enough to have salt caverns. Unit B is the thickest salt layer. It has a maximum thickness of around 90 meters. And unit A2 is the deepest, has a maximum thickness of 43 meters. I want you guys to note that the salt beds are dipping in the southwest direction. That means that the depth of the salt beds and thickness of the salt beds is not consistent throughout southwestern Ontario. So if you drill a well in Windsor or Goderich or Sarnia, you'll encounter salt beds at different depth and the thickness of salt beds will vary. Well, for Ontario, we are focusing on two major cities, Sarnia and Goderich. The reason is because they have adequate geology and there are wind plants nearby these cities and have good transmission network. In Sarnia, Unit B is 90 meters thick and starts at 610 meter depth. Unit A2 is 40 meters thick and starts at 750 meter depth. Whereas in Goderich, Unit B is 70 meters thick and Unit A2 is only 25 meters thick. As of now, salt caverns exist in Unit B and Unit A2 in Sarnia, and in Goderich there is one solution mine salt cavern made by sifter salt or compass minerals that exists in Unit B. So that was it for Ontario, and now I have one slide on Alberta because Alberta is also a very good place to implement CAES. In Alberta, salt beds are part of the Devonian Elk Point group in the Western Canada Sedimentary Basin. So if you focus on the figure on the right-hand side, there are actually four major salt-bearing units. The lower Lotsburg Salt, the upper Lotsburg Salts, the Cold Lake Formation, and the Prairie Evaporite Formation. The lower and upper Lotsburg Salts, as we discussed previously, are one of the purest salts as compared to the other formations. And this is because the salt has been recrystallized. In the lower Lotsburg Salt, the thickness can reach a maximum of 60 meters. In the upper Lotsburg Salt, the thickness can reach a maximum of 150 meters. The Cold Lake Formation is actually divided into two parts. One in eastern Alberta and one in northern Alberta. In eastern Alberta, the maximum thickness can reach 60 meters, and in northern Alberta, maximum thickness can reach 80 meters. And the Prairie Evaporite Formation is actually the least pure salt in Alberta, but it is the thickest. The thickness can reach from anywhere between 25 meters in southern Alberta to 300 meters in northeastern Alberta. So shape and size of salt caverns. Well, salt caverns can be made in different shapes and different sizes. The most common one is cylindrical shape. In Alberta, we can actually use single cylindrical caverns, which have a larger height. That's because the salt beds are thicker there. But in Ontario, we have to settle with either multiple cylindrical caverns or long horizontal galleries. Multiple cylindrical caverns, the only problem with these is that they're in the end they will be very expensive because each of the cavern will require a well, and wells are very expensive to build. But the benefit is that there are so many cylindrical caverns and they're easy to solution mine. Another option in Ontario is to build long horizontal galleries. That's because we have thinner salt beds, say around 25 meters to 30 meters, so we can build long horizontal galleries with around 800 meters to 1 kilometer in length, and the diameter can be around 25 meters to 30 meters. The issue with this is the solution mining. At this point, we're not fully sure how to solution mine a long horizontal gallery, but the cost will be relatively cheaper than multiple cylindrical caverns. The second phase of the geomechanical model is data investigation, or creating a mechanical earth model. Mechanical earth model is basically a collection of rock mechanical data, and there are 5 major components of MEM, and these are structural feature information, stratigraphy or lithological information, elastic properties of rocks, so rock strength parameters, and in situ stresses such as sigma 1, sigma 2, and sigma 3. There are 3 ways of gathering data for MEM, and these are core testing, well logging, and seismic tests. Well, core testing can be thought of as a magnifying glass of the geomechanical model because it takes rock information from a point in the wellbore, whereas well logging can be thought of as a glue between core testing and seismic testing because it takes rock information about 5 to 6 feet from the wellbore. And the seismic tests cover a very large area, say about 200 feet from the wellbore. So to get a better picture or to get a better ground truth, we need to actually perform all these 3 kinds of testing. And And even though core testing and well logging are relatively more expensive than seismic testing, they still need to be performed because they are needed to calibrate seismic models. Seismic testing alone will not produce adequate results. So before I move on to the next section, which is numerical modeling, I have one slide on the constitutive equation of salt. Mohammed has already described creep. For beginners, creep is just time-dependent deformation of rock salt under constant deviatoric stress. And there are many equations to model creep, and this is one of them. This is Norton's creep law. Mohammed has described these parameters in his presentation. So the third phase is numerical modeling of salt caverns. The objective of this phase is to make design decisions such as finalizing maximum and minimum operating pressures, finalizing the shape and size of the cavern, the depressurization rate, and finalize cavern spacing. While doing numerical simulation, we need to consider cavern closure, roof stability, and interbed slippage. Well, let's talk a bit about maximum and minimum pressure limits. As a cavern operator, during injection period, I would want to operate the cavern at maximum pressure to try to get in as much air as possible. And during extraction, I would try to operate cavern at minimum pressure so that I can extract the air for a longer time and produce energy for a longer time. However, maximum and minimum pressure have limits, and these are due to cavern stability issues. The first issue is roof failure. When we lower the pressure in the cavern, the supporting force for the roof might be decreased, and that can cause roof collapse. The second is cavern closure. Well, again, if we reduce the minimum pressure in the cavern, the deviatoric stress will increase, and that can increase the creep rate, so that the salt walls will start to creep in. The third is interbed slippage. Well, if we have known salt interbeds in the salt cavern, and if we lower the pressure in the cavern, the salt will start to creep, but the known salt interbeds will not respond to creep. So there will be a stress difference between the salt beds and the known salt interbeds. This can cause interbed slippage. The fourth one is, well, cap rock fracture. If we load up the cavern to a maximum pressure, then it can actually fracture the cap rock, and that is not good. So as you can see, I mentioned minimum pressure value a lot of times. Minimum pressure value, whether we build a cavern in Alberta or Ontario or anywhere in the world, is a very critical factor and must be considered. As a rough reference, maximum pressure should be less than 80% of the fracture pressure of the cap rock and the salt, and the minimum pressure should be at least 25% of the lithostatic pressure. This is just a rough reference because different government regulations will have different numbers, and different salt areas in the world will have different numbers, and we'll have to do numerical simulation to figure out the exact numbers. But the last phase is monitoring. Well, monitoring is a mandatory requirement by government regulations, and they're needed for insurance purposes. Monitoring provides important technical benefits, such as it can calibrate geomechanical laws and models, it can avoid cavern and well failure, and it can increase safety. The three major monitoring areas are subsidence monitoring, microseismic monitoring, and sonar surveying. Well, subsidence monitoring, the first one. Well, movement in cavern due to creep or roof collapse can transfer the strain to the ground, and it can form a shallow subsidence ball on the ground. And the caverns in bed salt are actually prone to subsidence. That's because in bed salt we tend to have cylindrical caverns with larger diameters, which can cause roof collapse. And in subsidence monitoring, there are actually 5 techniques. These are leveling monuments, or using GPS, using INSAR, extensometers, and tilt meters. The second monitoring technique is microseismic monitoring. Well, days before or even months before any major cavern collapse event, such as roof failure and any major damage, cavern does show some warning signs. And warning signs come in the form of fracture initiation or bedding of plane slip. And if we have microseismic monitoring in place, they can actually detect the warning signs. And if we can detect warning signs days or months before the actual event, then we can prevent the actual event. The important parameters obtained or interpreted from microseismic monitoring are location of the event, magnitude of the event nature, and slip direction. The last monitoring technique is sonar surveying. Well, in sonar surveying, sonar caliper tool is lowered in the cavern, and it measures the profile of the cavern using the sound waves. So the profile of the cavern can be measured in 2-dimensional, isometric, and 3-dimensional plots. Sonar surveying is a good cavern management tool because think about it. If we measure profile of the cavern today and then we measure once more in 10 years, we can actually calculate the volume change, and that will give us the creep closure rates. And the other benefits are it can calibrate finite element modeling, it can increase confidence in solution mining models, it can enhance safety by detecting any major damage in the cavern, and it can provide important inputs to the geomechanical model. Well, this was it for the geomechanical model. I want to conclude that there are 4 major phases, and they were geology, data investigation, numerical modeling, and monitoring. Right? If you have any questions.
Thank you. I don't have any. Thank you, Jay. I don't have any questions that have come in on the web, on my computer, so I'm opening the questions for anyone here. Dr. Fraser.
Just out of curiosity, how does creep under non-constant stress? Because you're defining it under constant stress.
Right. How is it under constant stress?
Creep is defined in a situation of constant stress when you're characterizing that property.
Right.
Right? In compressed air energy storage, you're going to be cycling, and the stresses aren't going to be constant. So in mechanical engineering, we'd be worried about things like fatigue. And I didn't hear anything related to fatigue here. I heard about, roof collapses and stuff and maintaining pressure. So I'm wondering about the cycling effects and where they might be included in the model.
I guess they will be included, but the pressure cycling effects are not fully understood in the geomechanics side as of now. And I actually read some articles about it, and it does say that cycling does affect it, but how much is not fully clear right now. And this equation, I guess you're talking about why is it constant deviatoric stress? Is that
Not why, just how would you modify it if at all for it?
How would I modify? Well, I don't have an answer for that, but yeah. I read some articles, could not actually come to a conclusion. But pressure cycling would eventually need to be added in the geomechanical models, that's for sure.
Thanks, it's good to know there's lots of good research that can be done.
Yeah.
The second question, this is not my field directly. You were talking about ground truth in your data investigation, but you don't really define it for those of us who are not familiar with the term. Could you define the ground truth that you refer to?
The ground truth, in my opinion, is how close you can get to the actual reality. That's the ground truth. Because when you do core testing, that's pretty much very close to the ground truth, as you can see in here. And when you do seismic testing, because you're doing it from the surface, you don't get the perfect data. And that's away from the ground truth, which is away from the actual reality. And that's why we need to do all these testing, core, seismic, and well logs, because you cannot do core testing everywhere in the subsurface. It will be too expensive, and it's not actually possible. So that's how ground truth can be defined by collecting all these 3 techniques and integrating them. You can reach closer to the ground truth, but of course you can never really measure all the points in the subsurface.
Yeah, and also the issue of scale.
Right.
In testing, you're limited to centimeter scale, whereas your cavern is hundreds and hundreds of meters scale. So going from the low scale to many orders of magnitude larger scale,
Right.
we have to kind of go through these well logging and seismics and then measurements as well, as you pointed out, in order to confirm our model. Question from Dr. Jackson here.
John, in the testing of cores,
Yes.
presumably you're going to be using them to get some initial measurements for your creep rate.
Creep rate. But creep testing is actually not a lot of companies have equipment to do it. But yes, creep testing is one of the tests which we will be doing.
So you'll be using a pretty sophisticated triaxial cell. I
Right.
presume.
Right. Right.
Okay.
The other equipment for creep testing is totally different than the other testing methods, and it's very sophisticated and very expensive. That's true.
Could you go back to the equation for the creep?
Yes.
Dr. Fraser, the left-hand side of the equation is actually epsilon dot. So it's a rate. So in other words, that does handle the different stress states. If you take that equation and plot it on a log-log plot, then what you have is a strain rate and a stress difference, sigma 1 minus sigma 3. And there's a straight line there with a slope of n, so that gives you the creep rate at different deviatoric stresses. Yes. Yeah. And a big issue that Mohammed referred to in the first talk is that exponent A in the equation, it's unique for every salt. It depends upon crystal size, moisture content, porosity, the amount of clay and other material that might be in the salt. So that does present a need to test your materials. It's not like a steel or something that you can, where you know your bounds are quite narrow. We have to really kind of do those tests to estimate those parameters, and then not push these laws, if you want to call them that, these behavior laws, beyond the range for which they were. By the way, some of these issues have led to real problems in mining, in salt mines. We've had salt mines collapse because people did not understand these issues.
So what is sigma 0? Sigma 0.
Oh, sigma 0 there is just a normalizing stress. It's taken to be the stress at which you have a mechanism change. The mechanism changes from a diffusion, fluid-assisted diffusion dominated creep to a more rapid creep mechanism. So it's kind of like we use it as a normalizing stress. Typically it's about 10 megapascals. Yeah. In other words, if the salt is at a differential stress less than 10 megapascals, it's following one creep relationship, so your exponent n is different. If you're at a higher deviatoric stress, you have a different set of mechanisms, so your exponent n has a higher value.
Right. Actually, Dr. Fraser, you made a very good point on pressure cycling, and there's also another category which is temperature cycling. I think these two topics, pressure cycling and temperature cycling, I have them in my report that I did that I made for this course, but I figured out that they're not well researched, and research is still going on in those topics at this point.
I think what the basis of information that we have today is two small compressed air energy storage operations, one in Germany and one in the United States. And to their surprise, and to our, in a sense, relief, it appears that the cycling does not affect the salt in a negative manner. It actually kind of maybe even anneals it to give you a more uniform behavior. Our issue is somewhat different. because of the limited height of our salt beds, particularly here in Ontario, we will very likely have roof rocks exposed in the roof. Maybe not for the full cavern span, but for some portion of the span. And the cyclic loading on those roof rocks is simply not understood. There is no information that we have managed to glean from any source on that issue. And yet, that roof span is a critical factor in the performance of the axisymmetric circular caverns. If you could go back to your diagram with the different cavern shapes. So for these circular axisymmetric caverns, the wellbore penetrates here in the middle of the roof, so that a roof collapse would impair your casing and your well operation completely. Interestingly, for long horizontal caverns, your wellbore actually comes in at one end, like this. And that means that roof falls are not so critical in well impairment for a horizontal cavern as they are for a vertical cavern. So the design parameters are different. And we hope to, during our research, clarify these things somewhat. But remember, we're always dealing with uncertainty at various scales.
I just want to point out one more thing, which is in Huntorp, they say that pressure cycling has...
Huntorp, hang on. Huntorp is the CAES project in Germany.
Right.
Okay, it's near Bremen in northeastern Germany.
Right. They actually have two caverns there. They say that pressure cycling has not affected their caverns in whatever years they have done production, but their numbers are very conservative for their maximum and minimum pressure limit does not have much difference. But in the case in Ontario, we'll actually be using high numbers for maximum pressure and low numbers for minimum pressure. So in our case, we'll have to deal with pressure cycling problems.
Yeah, the kind of projects that we envision in Ontario and Saskatchewan and Alberta in bedded salts have simply never been, the kind of pressure limits have simply never been looked at in terms of cyclic loading. So this is quite novel. In other parts of Canada, like New Brunswick and Nova Scotia, those two provinces, the salt is not bedded salt purely. It's domal salt, similar to the existing compressed air operations in the world. Or in the case of New Brunswick, it's a very thick salt cord anticline, so that you can get vertical distances enough to put in a vertical cylindrical cavern like you see on the left of this picture. But if we're going to have compressed air storage, for example, in Chatham, Ontario, then either we're going to have the small circular caverns, maybe 30 meters high, 40 meters high, or longer horizontal cylindrical caverns that can have volumes up to 250,000 or 500,000 cubic meters. These numbers actually are not large. There is a compressed air energy salt cavern facility being planned in Texas in a domal salt, and their working volume is going to be on the order of 1.1 million cubic meters. And that will give them a capacity through a 24-inch casing of 320 megawatts, just to give you some numbers to think about. So these are big, expensive wells to give you the flow capacity without loss of energy. Thank you, Jay.